Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures on computer architecture. We have been looking at design of the control unit, and specifically we have been looking at pipeline control. So, in the previous class we looked at hazards, handling of hazards, and we also looked at how the MIPS pipeline has been designed. So, this is what we have been looking at in the previous lectures. In today's lecture, what we would look at would be more details on handling hazards in the pipeline. We have talked about hazards and we have talked about how hazards are a problem in the pipeline. So, what we will look at is how these hazards are actually handled. What is it that we need to add in the pipeline design in order to handle these hazards. So, that is what we will take a look at today, and we will also see if we can take a look at other issues in the pipeline, typically what happens when exceptions occur. So, we will take a look at this a little later. So, we will first start with handling hazards. So, if we look at handling hazards, let us take this simple sequence of instructions that we have here. So, we are talking about say 5 instructions here. This is sub instruction and then an add instruction, an OR instruction, an add instruction, and then a store. So, this sub instruction is adding to registers 1 and 3 and storing it in register 2. Okay. And then this register 2, the contents of this register 2 are used as inputs, as source operands for the instruction AND, for the instruction OR, for the instruction add, and also for this instruction store. Okay, these are source operands. So, which means that once this sub completes, only then the output will be available for others to use. So, we know that in our pipeline mechanism this can cause a hazard, because until this completes we will not be able to allow these instructions to execute. So, we said that we can use something called forwarding. Forwarding is passing the value which is there at the output of some stage to the other instructions which are there, which require it in some other stage. Okay. So, this is what we said is meant by forwarding. So, forwarding is, that is, remember that when the sub instruction comes out of the execution stage, that is completed execution, the value actually is available in an intermediate register. So, from that register if we can forward it to these instructions here, so then we know that with forwarding we can without stalling on whenever we have this kind of a hazard, we will be able to make the pipeline progress forward. Okay. So, how do we determine when to forward and how do we do the actual forwarding? So, that is what we are going to take a look at now. So, look at this sequence again now. As the sequence of instructions flows through the pipeline, this is what you are going to find. So, you have the sub instruction coming in clock cycle 1 in the IF stage. Remember our 5 stages: IF, ID, EXE, memory access, and then the write register. Okay. So, in the instruction fetch stage, instruction memory is accessed. So, sub instruction will be in the instruction fetch stage in this clock cycle 1, go to ID clock cycle 2, EXE stage clock cycle 3, and then mem stage in clock cycle 4, and clock cycle 5 it will go into the register writing stage. Okay. Now, let us look at the other instructions here. Add instruction is coming in clock cycle 2, OR instruction will come in clock cycle 3, the add will come in clock cycle 4, and this store will come in clock cycle 5. Now, let us look at when these different instructions require the value that is produced by the sub instruction, the first instruction. Now, the actual register value will be written in clock cycle number 5. This is where it will actually be written. Okay. So, you can see that writing it in clock cycle number 5, but let us look at when the AND, OR and OR add instructions actually need to use that value. The AND instruction requires it in clock cycle number 3, okay, because it will be reading the registers in this clock cycle, or if it is going through the pipeline will require it in clock cycle number 4, the add will require it in clock cycle number 5, and then the store will read it in clock cycle number 6. Now, you can see that reading it in clock cycle number 6 is not a problem at all, because it will be already written to register in clock cycle number 5. Okay. So, reading it in clock cycle number 6 is not a problem. Okay. Similarly, even clock cycle number 5, let us assume that we will write in the first half of clock cycle 5 and read it in the second half of clock cycle 5. Okay, even this is not a problem, but it is these two instructions which will cause a problem, because you are writing it in later cycle, but you need to read it earlier, right. So, this is a problem that we have. Now, we are saying that this problem can be solved with the help of forwarding. So how do I say that this can be solved with the help of forwarding? All we are trying to say is this value which is written to the register is actually available at the end of clock cycle 3, but only thing is it is available in this inter stage register. Now if you look at this, this is the exe stage and this is the mem stage. So in the ex/mem stage register, which is what I have here, in this stage this register value is actually available at the end of clock cycle number 3. So now from this register at the end of clock cycle number 3, if I can forward it over here, right, from here to here, this red line here, this indicates that we are forwarding from here to here. So if I can do this forwarding from here to here, then this AND instruction will be able to use that value and proceed forward without any stall or without any block to the pipeline. Similarly, now this OR instruction requires the value when it is going for execution over here. Okay. So now this is the value that it requires here. This value again, as the sub instruction progresses through the pipeline, the value of register 2 would have now moved to this interstage register. Remember, because when we go from one as it progresses through the pipeline, the value will be sent from one register to another register. So it will be available in this register. So from this register, I will need to forward it to this, to the input of the ALU. So you can see that for the AND instruction, forwarding has to take place from this register, that is from exe mem interstage register to the input of ALU, and for this OR instruction to work correctly, you need to forward from the mem write back interstage register to the input of the ALU. Okay. So we need these two paths that need to be added. If you have these two paths added and if you do this forwarding correctly, then without stalling you will be able to proceed. Okay. So this is what we need to look at, how this can be actually done. So let us look at how we will actually detect this, the forwarding of the operands. Okay. So let us look at this. So what is it we have to do? First of all, what is important is that the register numbers have to be passed along the pipeline, because as I go through the pipeline, I need to know what is the register to which this particular value has to be written or where it is read from. Okay. So that information has to be passed on along the pipeline. So you will see that we need to have some way of denoting it. So for instance, let us denote it like this. So we will denote each interstage register by the two stages that it connects. Okay. So when you say ID/EX, it means that we are talking about the interstage register which exists between the ID stage and the EX stage. So ID/EX dot register RS, if we specify it like this. So this, what we are actually referring to here is, we are saying that this is register number for RS which is sitting in the IDEX pipeline register. So remember, we are using the terms RS and RT to denote the source registers and RD to denote the destination register. Okay. So since we are looking at 3 operand instructions, we have 2 source operands and 1 destination operand. We are denoting it as RS, RT will denote the source registers and RD will denote the destination register. So this information of which is the source register and which is the destination register for that instruction will have to be carried along in the pipeline. So which means it will go from one pipeline register to another pipeline register. Okay, that is important. Second is the ALU operand register numbers in the EX stage. Okay, so they will be given by ID/EX dot register RS, ID/EX dot register RT, and so on. So this is how we are depicting it. Okay. How do I detect a hazard using this? So when is a hazard to be detected? Just go back to this pipeline here. Now when will I detect a hazard? Let's take this second instruction here. Now this second instruction is going to cause a hazard if you do not do forwarding, right? So how do I detect that it will cause a hazard? I will be able to detect that it will cause a hazard by looking at the source registers in this interstage register and compare it with the destination register in this interstage register, which is what we are doing here. That is EX/mem dot register RD, destination register which is there in the EX/mem interstage register, pipeline register. If this value, if this destination register is equal to ID/EX register RS. Okay. So ID/EX, that is I am talking about, this is the ID stage/EX stage. Okay, the one which exists between ID and EX. The source register here, if this source register matches this destination register, okay, then I will have to forward from the EX/mem pipeline register. Okay, because EX/mem is where the RD value, the value will be available. So that value will have to be forwarded to the input of the ALU. So, you need to compare this ex slash mem dot register rd is equal to id slash ex dot register rs. Either it may be rs or it may be rt. Remember, there are two operands, right? So, we need to check for both the operands. So, just as you do the check for this register rd being equal to rs, you also check for this register rd being equal to rt. So, if either of these two operands matches the destination register which is there, then we know that there will be a data hazard, and therefore, we need to do forwarding from the ex slash mem pipeline. Okay, this is one case. Second case that we need to look at is, remember, we also forwarded from this stage to the next instruction. Okay, so how do I detect this forwarding sequence? So, to detect this forwarding sequence, remember, I am no longer looking at this position, but I am now looking at this position. If this value is equal to the value that I have over here, then I will need to do the forwarding. So, that will be depicted in the following manner. Now, we are looking at mem slash write back register. Okay, the mem slash write back dot register rd, the destination register here, is equal to the id slash ex dot register rs. That is, before it goes for execution, I am checking whether the source value rs or rt is equal to mem slash write backs rd. If this is equal, then I know that I need to forward from the mem slash write back pipeline register back to the exe stage. Okay. So, this is how you detect the need to forward, and then we will do the forwarding. There is something more that we need to check when we are doing this forwarding. It is basically the following, that is, only do the forwarding if the forwarding instruction will actually write to a register. If it was not writing to a register, so then we really do not have to worry about it, right. So, we check whether ex slash mem dot register write, a control signal called register write, is present in that ex slash mem stage, or similarly in the mem slash write back stage. That is, this check that we did over here. This check obviously is valid only if this value that you are writing to is actually going to be written to a register, right. So, we need to check whether the register write signal is active or not. So, you will have to also check whether these two signals are active, and only if rd for that instruction is not 0. So, we also will check whether ex slash mem dot register rd is not equal to 0. This condition and this condition that we are checking over here, we can determine how the forwarding logic has to be designed. So, forwarding logic design, you will see, essentially is basically all these comparisons put together. Okay. So, this is what we do. So, let us look at what the forwarding path will be like. Okay. So, remember, where are we forwarding from? There are two places from which we forward back to the ALU. Okay. One is from the exe mem, this is our path over here, and then other is the mem slash write back path. Okay. This is one interstage register, this is another interstage register. So, from this interstage register, I will forward back here. Okay. See, there is something called a forwarding unit over here. So, I will forward here, or from the mem slash write back stage, you will do the forwarding here. So, either of these two stages we will forward, and from here we are sending it either to the input of the ALU. So, whether you are forwarding it to the A input or the B input. So, that will be determined based on whether it is RS or RT that is going to match. So, you will look at this RS or RT, these two values also come in here, and based on this check that we just talked about, this forwarding unit will forward it either to A or B. Okay. So, you can see that if I am forwarding it to A, you can see that this path here, right, from the output of ex slash mem comes back over here and is given as one of the inputs to the mux. Okay. You can see that this goes both over here as well as over here. Depending on whether I am forwarding it to this input or to this input, this control signal will choose the correct value, and then we will be able to forward. Okay. So, this is what we will do. Take a short break and then come back and continue with this. Welcome back after the break. So, we were just looking at this forwarding path and how the forwarding gets done. So, as I said, forwarding gets done from either the output of the ex slash mem stage or the mem slash write back stage, okay, back to the input of the ALU. So, this is where the forwarding is done for this particular set of instructions. Now, coming to the forwarding conditions. So, we just talked about what conditions need to be checked. So, I am just kind of putting all those together here in this slide. So, what we are looking at is, if we are looking at a hazard which will be solved by forwarding from the EX stage, so I am calling it as EX hazard. So, let us look at the conditions we need to check for. If EX slash mem dot register write and EX slash mem dot register RD not equal to 0. that is we are checking whether we are doing a register write and the destination register value is not equal to 0, then you are checking and you are also checking whether register rd ex/mem dot register rd equal to id/ex dot register rs. We are checking for the first source operand. If this operand is equal, then I am setting forward a. Okay, so let us say I am setting that value to 1 0. If ex/mem dot register write and ex/mem dot register rd not equal to 0, same condition as what we had in the first case here, and now we are checking for whether the destination register matches with the second operand register, that is register rt. So if this is equal, then I know that I have to forward it to b. So let us say forward b now is set to 1 0. This is a ex hazard checking. Similar thing we need to do for a mem hazard checking, that is now we will be checking from the mem/write back dot register write stage. So mem/write back dot register write and mem/write back dot register rd not equal to 0, and if mem/write back dot register rd is equal to id/ex dot register rs. If this condition is valid, then you are setting forward a is equal to 0 1. So this condition tells you that we are forwarding from the mem/write back stage. Similarly, we do a check for the second operand. So you can see we had rs here, now we will have rt here. Okay. So this shows that you are now checking for mem/write back dot register rd is equal to id/ex dot register rt. So then we are forwarding it to b. Okay. So forward a or forward b, which is the one that needs to be set. So that is what we are checking in this case. Now there is another forwarding condition that we need to look at, which is when we are using the value of a load instruction. Let us take this sequence now. I have a load instruction, load from some memory location to register 2, and then I am using that value in the next instruction. So I have an AND instruction here. This AND instruction is using the value which is to be provided by this load. Now remember that the load instruction would have got the value, the destination which is to be written to the destination register only at the end of the memory stage, that is only at the end of clock cycle number 4. If we take start from clock cycle number 1 here, IF, ID, EXE, memory access and then the writing register. So you can see that over here is when the memory access takes place. So only at the end of clock cycle 4 I will get this value. Now here if you see this AND instruction requires the value at the beginning of clock cycle 4 or at the end of clock cycle 3, because this is where it enters into the EXE stage. Now naturally we know that this operation cannot be allowed to happen because there is a hazard. The value is not available. You can forward it only ahead in time, right? You can't forward it back in time. So this particular instruction, this AND instruction will have to be stalled for at least 1 clock cycle. Once you stall it for 1 clock cycle, then in the subsequent clock cycle we can do the forwarding and allow it to go through, but otherwise you will have to stall. Okay, this is something we need to remember. Now look at the next instruction, the OR instruction that you have here. This OR instruction actually requires it in this clock cycle. So if the AND had progressed forward, you will be able to do the forwarding here. But if we block the AND, if we stall the AND, naturally all the other instructions also will be stalled. With the stall, let us look at how the pipeline will move forward. So to do that, you have to first of all detect the stall that needs to take place. Okay. So and the stall will happen whenever we have a load instruction whose output is to be used by an immediately following instruction. So that is what we need to understand. Okay. So let us see how we do this stall. To do the stall, what we do is we check when the using instruction is decoded in the ID stage itself. Okay. So when I talk about decoded in the ID stage, that means I am talking about using the information which is there in the IF/ID registers. Okay. So the ALU operand register numbers in the ID stage, okay, will actually be given by these registers, that is in the IF/ID pipeline register, register RS and register RT. Okay. These are the operand registers. So now what we do is a load use hazard will occur when ID/EX dot mem read, that you are going to be doing a memory read in the next clock cycle, and that instruction is now in the ID/EX stage. See, the instruction we are looking for, the one which is going to use, if it is there in the IF/ID stage, then the load instruction should be present in the ID/EX stage. So you check whether for the instruction which is there in the ID/EX stage, where the mem read signal is active. So, id slash ex dot mem read and id slash ex dot register rt is equal to if slash id dot register rs. That is, the register rt, the value is there in register rt is equal to this register rs, or if id slash ex dot register rt is equal to if slash id dot register rt. If this condition is met, then you say that we are detecting the hazard and therefore we will stall. So, how do we stall? Basically what we mean is we will insert a bubble. Okay. So, we will look at how the stalling is done, okay, and how exactly we insert this bubble into the pipeline. Okay. So, now that we have detected that we need to stall, let us look at how the stalling actually gets done. Now, to stall the pipeline, this is what we will do. What we have to do therefore is, first to stall the pipeline is, we will force the control values in the id slash ex register to 0, okay, which means when this instruction, when whatever values have been written here, when this moves to the ex stage or the mem stage or the write back stage, okay, they are actually turned into no ops. A NOP is normally an instruction which says that no operation is taking place. Most processors will have a special instruction called a NOP instruction, okay, which essentially does no operation, but it can be used to for these kind of purposes, to flush the pipeline or to just fill in an idle instruction. If you want to have idle cycles to be inserted, we make use of this NOP instruction. So, the ex, mem and write back stages will be converted to NOP instructions. Okay. So, and what we also do is you prevent the update of PC and the if slash id register. So, which means you are holding on to that instruction, the previous instruction is continuing to be there in the same stage. The using instruction, okay, will be decoded again, okay, and the following instruction is fetched again. That is what we mean when we say that you are preventing the update of PC and preventing the update of the if slash id register. Okay. So, the same instruction will be decoded again and the following instruction will be fetched again. So, one cycle stall, okay, you will do it for one cycle. If you do it for one cycle, we have a one cycle stall. So, this one cycle stall will allow the mem to read the data for the load instruction, okay, and you can subsequently forward to it in the ex stage and we can continue with the execution. Okay. So, remember this, why we are doing this forwarding here. We will come back to the pipeline figure. So, if you look at this pipeline figure here, so let us see what we are doing here. So, I have this load instruction, I have an AND following it which is going to use this load. Now, this AND we are now converting it into a no op, okay, so which is what we are showing here. So, this bubble here indicates that as this instruction goes through this pipeline, it is actually converted into a no op, nothing will actually happen here. So, in the next clock cycle, okay, in the CC3, in the next clock cycle, and again will continue to be fetched, right, and then it will go into the decode stage and then it will go into the exe stage and then the memory stage and then the write back stage. So, you can see that one clock cycle there will be a delay and then the OR instruction will go in the next clock cycle and then you can see the instructions flowing through the pipeline. But even here, when this AND instruction moves to the exe stage in the next clock cycle, now it needs the value from the register. Now, register value is not yet been, it cannot read it in the previous clock cycle, but the value of this load is available in this register, that is at the output of the mem stage and before the write back stage. The mem slash write back register is available. So, if you can forward it from the mem slash write back to the input of the ALU, then this AND instruction can proceed forward. Okay. So, this is what we meant when we said that you can subsequently forward to the EX stage. Okay. So, we forward it from the output of mem to the input of EX and with one clock cycle stall, you are able to handle this particular hazard that has occurred. Okay. And the other instructions, the OR instruction, when it goes through, you see that it is anyway going to read it in the next clock cycle. So, it will be able to go ahead without any problem. And you can also see in this particular sequence of instructions, I have an AND instruction which is writing to register 4 and then I have an add instruction which is reading from register 4. Okay. So, between this AND and this add again there is a dependence. So, that also is handled by means of forwarding. So, once we understand how this forwarding is in place, we will be able to figure out how many instructions will be able to move without any stalls and which are the instructions which will actually have to be stalled. Okay. So, you can see how this stall or bubble in the pipeline is handled by just making this as a no op. More accurately, this is what will happen. So, when you say that the AND becomes a no op, so remember when the AND becomes a no op, you already had the AND actually is being stalled in the ID stage. Okay. So, what is actually happening is this is the actual picture, that is this instruction will continue to be in this ID stage, that is it is doing the register read, okay, and the OR instruction which is following that will be stalled in the IF stage. So, this will now continue to be in the IF stage. Okay. So, you can see that in the next clock cycle is when this will move to the EX stage and then move to the memory stage and the write back stage. So, the bubble meanwhile in the previous clock cycle, that is in clock cycle number 4, right, in clock cycle number 4 is when AND should have come into the EXE stage. So, that particular cycle you have no operation taking place here. So, similarly in the next clock cycle there is no operation taking place in the memory access stage, and in the next clock cycle there is no operation taking place in the register write stage. Okay. So, this is what is happening here. Okay. So, this is how the actual stalling of the instructions will take, that is they will continue to be in the previous stage and then move on to the next stage in the subsequent clock cycles. Okay. So, this is how the stall or bubble in the pipeline will be handled. So, now this is the complete picture that we have with all the hazard detection and the complete data path that we have here. Okay. So, what we are doing is, now remember from the IFID stage, IDEX stages, EX mem stages and the mem write back stages, from these stages, okay, we have information coming back here to the hazard detection unit. So, we are introducing a new unit called the hazard detection unit, which will take inputs from all these stages, okay, all the different registers that we talked about now, IF/ID dot register, RS, RT, RD and so on, right. All this will come as input to this hazard detection unit, and from here you will have control signals which are generated to the various muxes and so on in order to do the forwarding and in order to do this stalling of the different instructions. Okay. So, this is how the data path will have to be modified in order to do the hazard detection as well. Let me quickly summarize what we have been looking at in today's lecture. So, what we looked at is handling of hazards in the pipeline. Of course, we have been looking at the MIPS pipeline. So, handling of hazards in the pipeline is something we have looked at, and specifically we have looked at the data path and the control signals to detect the hazard and forward the operands. Okay. So, how is it that we identify the data path? Okay. How do we generate the control signals? This is what we have looked at. So, we have identified that there are two forwarding paths. One is especially to handle data hazards. One is from the EX/mem stage to the input of ALU, and another is from the mem/write back stage to the input of ALU. What we have also seen is, even in spite of this forwarding path, still stalls may be required. And we saw that whenever you have such stalls, you will do that stall by basically converting the stalling instruction to a no-op and pushing it out of the pipeline. This is what we have looked at, that is, when a hazard occurs, how do we handle it with the help of forwarding and or by means of stalling. Questions to review the content of today's lecture. Question number 1, how does forwarding help handle hazards? Question number 2, in the MIPS pipeline, when will forwarding help? Question number 3, why do we need a stall in the case of a load instruction immediately followed by a using instruction? Question number 4, what are the conditions to be checked for forwarding from EX/mem stage to the input of the ALU? Question number 5, how is a bubble introduced in the pipeline? Thank you.